All right, so we're going to use the sandwich theorem to prove this limit. And first off, what we're going to do is we're going to start off saying that what we're looking at here is a circle with a radius of 1. So we're just going to say that the distance from the origin there to the edge of my circle is 1, which also tells us that, what could you say about this diagonal distance here?
It's also 1.
Also,
it equals 1.
Also a radius, it's also 1. Perfect, good. So now what I want to do is I want to focus in on the idea of what the sandwich theorem is. The sandwich theorem is, it's a theorem that's helping us prove limits, but we have to have a specific function in the middle. We need to have our function sine x over x in the middle. And we also need to have a function that's always less than or equal to that function. We need to have another one that's always greater than or equal to that function. So we're going to need to write out a series of inequalities here. And I'm going to sort of guide us along the path to get us started here. We're going to take a look at this. Oh, that doesn't look very good. We're going to take a look at this triangle right there. We're also going to take a look at the portion of the circle, the sector of the circle right there. And we're going to look at this bigger triangle that is outside of this circle. And we're going to try and determine the areas, and it seems kind of arbitrary, but that's what we're going to do, is we're going to determine the areas of each of those pieces of this picture. So in order to do that, what we're first going to do is we're going to call this angle right here angle x, and we're choosing x because we got sine of x up here in our limit, right? And that's the angle we're using is angle x. So if this is a unit circle with a radius of 1 and this angle here is x, let's see what all we can label. Can we label this vertical distance right here?
Sine of x.
Sine of x, exactly. That vertical distance should be sine of x. And we know that because if this is a unit circle, then the y coordinate, which is how high up we go from the x-axis, is always equal to sine. So that distance should be sine x. This distance here should be cosine x. Even though that's not part of one of my triangles, we're still going to use that as cosine x. Might as well still label it. But already we should be able to tell what the area of the blue triangle is, right? Because what's the area of a triangle? The area of a triangle is just 1/2 base times height. The height of that triangle is sine x, and the base of that triangle is
1.
Just 1. So the area of that triangle should just be 1/2 of the base, 1 times sine x. Everybody agree that that's the area of the blue triangle?
Yeah.
Yep.
All right, cool. Now let's talk about the green triangle. We know what the base of the green triangle is, right? The base of the green triangle is
1.
also 1, right? But what about the height of that green triangle? What is this?
Tangent of x.
It's tangent of x. Why is that tangent of x?
Because tangent's opposite over adjacent, and since the adjacent side is 1, that's just the opposite side.
Exactly. Tangent of the angle, right? There's a right triangle here. Tangent of this angle x is the opposite leg over the adjacent leg. The opposite leg divided by 1. So if it's tangent x equals something over 1, that something has to be tangent. So over here, I'm going to write that the area of that green triangle is 1/2 tangent x. Now for the piece of that circle, the sector of the circle we've got there. How do we determine the area of that? Any thoughts on that? How do we determine the area of an entire circle?
Pi r squared times
Pi r
the
squared.
sector, or the angle of the, or like the percent, or like the proportion of the circle that it is.
Right. So the full circle is just the 1/2 pi r squared, right? And we're going to multiply, yeah, Nadine, you're right. You wrote that in the chat. We're going to multiply the area of the circle by the angle divided by the full 360 degrees. And when we do any sort of real calculations with area, we have to use radians. So we can't actually use the full circle divided by 360 degrees. We're going to have to use the full circle divided by, or not the full circle, but the angle divided by 2 pi. So if we take the area of the entire circle and we multiply it by our angle out of 2 pi, that should be the area of the just that one sector of the circle, right? Because the fraction of the circle that we have is x out of 2 pi, and the area of the whole thing is 1/2 pi times the radius squared. What's r? R is just
1.
1, right?
Yeah.
So, oh, why do I have a 1/2 in front of that? Do I keep saying that the area is 1/2 of pi r squared?
Yeah.
That's weird. I don't know why I said that. Sorry, I'm a little out of sorts this morning. Just, yeah, a little out of sorts. Then we got pi r squared there times x over 2 pi. I don't know why would I have said 1/2 pi r squared. That's just weird. I looked at it when I had it written there and it didn't make any sense. So the r value is just 1, right? And so r squared is just 1, and the pi's are going to just cancel out. And so we're just left with this x over 2 piece in the middle. Maybe I was just thinking that they all have halves in front of them, so I put a 1/2 in front of that. Who knows? Losing my mind today. So what is the relationship between the area of that blue triangle, the area of the sector of the circle, and the area of the green triangle?
The green's bigger than the red, which is bigger than the blue.
Exactly, right? We know that this must be true. And this now looks like an inequality that we could use the sandwich theorem with, except that the thing that we need to have in the middle is supposed to be sine x over x, and x over 2 is nothing like sine x over x, is it? Other than the fact that it's got an x in it. So first off, I can get rid of all these halves, right? Apparently, I'm really into having a 1/2 in front of everything today. So we'll get rid of all the halves by multiplying everything by 2. And look at this as sine x is less than or equal to x is less than or equal to tangent x. Everybody feel about that? Feel okay about that?
Yep.
All right, cool. So if I want to turn the center of this, the middle piece of this, into sine x over x, first thing to do is just to introduce the sine into it. I'm going to divide everything by sine, because if I divide everything by sine, the middle is going to become x over sine x, and I can just take the reciprocal then, and I'll have sine x over x in the middle. Does that sound good to everybody?
Yep.
Cool.
Yep.
So let's divide those all by sine x. And the left-hand side is just going to become 1. Middle side stays as x over sine x. And using a little bit of trig, you should be able to tell me what tangent x over sine x is. It should become what?
1 over cosine.
1 over cosine x, or we could write it as secant if we want, but 1 over cosine sounds good to me. And then what do we say we need to do? We just need to flip all of the pieces of this. So the reciprocal of 1 is 1. Reciprocal of x over sine x is sine x over x. And the reciprocal of 1 over cosine is cosine. When we take the reciprocal of every piece of an inequality, what happens to the inequality sign? They flip. Yep, they just flip. So these are going to become, yeah.
Why do they flip? Is it because I thought they only flip when you multiply or divide by a negative?
Yeah, or if you take the reciprocal of both sides. So if we take, I'll show you. Think about something like, you know, what do you got here? You got 1/2 is less than 2/3, right? Well, that's a 2. If I would take the reciprocal and a 3/2, what sign do I need to put in there? The 2 has got to be greater than 3/2, right? Anytime you take the reciprocal of it, it always, you know, you'll see that it always flips. Anything you put in there, it always will end up flipping. Let's see here. So it's got to flip. So we did that, and now we've got the function that we want sandwiched between two other functions. Cosine x is always less than or equal to it, and 1 is always greater than or equal to it. And if we were to go back real quickly and look at Desmos again, right, we had sine x over x, and if we have cosine x, and if we have just 1, I think I'm going to put y equals 1. On the interval now, on the interval very close to x equals 0, we can see that this is always true. 1 is above our sine x over x, and the green one is below it. Now, in other places over here, clearly they intersect and go past each other. But where we're looking right now, which is simply in the first quadrant, right? We're just looking in the first quadrant here. Any of these values, this is certainly true. Everybody good with that?
Yep.
Yep. All right, cool. So now, if we want to look at this, the limit as x approaches 0 of 1 is what?
1.
1.
1, right? Because the limit of a constant is a constant. And the limit as x approaches 0 of cosine x. Well, what do we do anytime we have a limit? We just plug the value in. What's the cosine of 0?
1.
1. And so we've now shown that the function that's sandwiched in between them, sine x over x, also has a limit of 1. Right. Any questions on that? Let's see how we apply the sandwich. Yeah, question?
So, okay, during like an exam or like just anything, if you just use the sandwich theorem to prove something, then how do we know what to use?
Yeah,
if we're not given like the diagram.
Right. So I'm not going to do that. You don't need to worry about that. I'm not going to ask you to use the sandwich theorem to prove something unless it looks, remember these ones we were doing the other day? It might look like this, but I'm not going to just give you some random function that you've never seen before and ask you to use the sandwich theorem to prove it.
Okay.
You don't even need to worry about that. Yeah. Any other questions on that?
Where did the x over 2 come from?
So the x over 2 is the area of this red sector of the circle. So if we take the area of the entire circle, that's pi r squared. And if we take the fraction of the circle that this sector is, it's the angle divided by 2 pi radians. So if I take the fraction of the circle that I have, x over 2 pi, and multiply it by the area of the full circle, then the the r squared, since r is 1 on this circle, that's just 1. And the pi over the pi cancels out. And then you've got an x over a 2 is all that's left. Does that make sense?
That makes sense.
Cool. Awesome. So, so that's where we're sitting now with this, is we've got this limit as x approaches 0 of sine x over x is equal to 1. What about x over sine x? It's sandwiched between two other functions also. As x approaches 0, this limit is still 1, right? And what about as x approaches 0? Is this limit also 1? 1 over cosine x?
Yes.
Yes.
It is. So we could also say that the limit as x approaches 0 of x over sine x is equal to 1. And so for right now, we can get rid of this here for a second. I want you to make sure that you commit those two to memory. The limit as x approaches 0 of sine x over x equals 1, and the limit as x approaches 0 of x over sine x equals 1. These are two that you're going to need to know, and you're going to need to use them over and over and over again. The sine x over x one comes up a lot more often, but the x over sine x one comes up as well. So make sure you commit those to memory. I will not ask you to prove these limits anymore using the sandwich theorem. Now that we've done it, and you should know. Sound good?
Yes.
All right.
Yep.
Cool. So what we're going to do for the next 20 minutes or so probably is we're going to take a look at some limits that we can use that known property that the limit as x approaches 0 sine x over x equals 1 to solve some limits that are similar. So we're going to start with the limit as x approaches 0 of sine 5x over x. Give me 1 second. I got to go tell my kids to be quiet. So I'll be back in half a second. Sorry about that. My 7th grade son seems to think that if he gets dropped from the class during the middle of the Zoom meeting, he doesn't have to call back and join back into the class. Okay, then I got the 7-year-old who's on his quote unquote recess break right now. Perfect. Good timing. All right. Are we ready?
Yep.
Can you guys can hear me again complaining about children?
Yep.
I wouldn't recommend it. All right. So we got the limit as x approaches 0 of sine 5x over x. This is very similar to the one we were dealing with before, right? Looks similar. Be nice if we didn't have to like draw out a circle and like a couple of triangles and find the areas of those triangles and the area of the sector of the circle and use the sandwich theorem. It'd be nice if we could just use that property. What if we turned this denominator into something that looked the same as the argument of the sine? What if we turned it into a 5x? Do you think that might help?
Yeah.
All right, let's do that then. So the limit as x approaches 0 of, let's see, sine 5x. Can I just make this 5x in the denominator?
No.
You have to
No.
multiply the top by 5x too.
Well, just by 5, because I already got the x in the denominator. But yeah, we multiply the top and the bottom both by 5, right? So then this sine 5x over 5x piece of it right here looks real nice, except that I don't have that one proved. I have the one proved with sine x over x. Plus, additionally, I've got this extra 5 sitting out here that's kind of in the way. But we have a rule about constants in front of a function, don't we? Within a limit, what can I do with a constant that's sitting in front of a function?
You can take that
Inside of it.
You just
bring it
push it
out.
outside.
Push it outside. Perfect. So now I can ignore that 5 for now. I'm just going to throw it out in the front. And now I'm just sitting here looking at something that is very, very similar to what I had before, except rather than it just being x and x, it's 5x and 5x. Is it okay? Can I just assume that this is 1, or is this 5, or is it like a 5th, or who knows? Any thoughts on that?
Well, I would think it'd still be 1 because the sign of any number would still be 1.
The sign, yeah, we're still going to get some. Yeah, it's questionable. So it is 1. I'll tell you, it is 1, but we got to prove it. We got to have a way to prove that. And anybody have an idea of how we can actually prove that it's still 1 without doing the whole sandwich theorem thing, without doing the squeeze theorem and the circle and the sector and the blah, 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 and way too much work? Any ideas?
Nope.
No, we can't just say it's 1. I mean, we could, but that's kind of unfair. All right. What about, let's see here. What if we made a substitution? What if I turned the 5x into some other variable? Could I do that? Somebody's typing in the chat. Yeah, simplify it down to sine x over x. So we can't quite just simplify it down because we can't cancel out the 5 and the 5 here. It'd be nice if we could cancel out the 5s, but since that's within the sign, we can't divide those out. Somebody had mentioned that in the chat. So what we're going to do is we're going to make a substitution, and we're going to let u equal 5x. So what's that going to give me? It's going to give me 5 times the limit as x approaches 0. Well, if we're turning this into u's, we might want to deal with this in terms of u. So that's going to give us sine u over u. You guys agree that that becomes sine u over u if I let u equal 5x?
Yes.
Okay.
Yep.
So what about the limit and what it's approaching? If u is equal to 5x and x is approaching 0, what does that tell you about u and what u is approaching?
It's also approaching 0.
It also ought to be approaching 0, right? I mean, if if x is approaching 0 and u is 5 times 0, then I should end up with u approaching 0 as well. And so with a simple variable substitution, I've now turned this into the limit as u approaches 0 of sine u over u. And this is the exact limit, other than the fact that these are u's instead of x's. That doesn't matter. I can name an angle anything I want. This piece inside the bracket should still just be 1. And so the result should just be that constant I pulled out, 5 times the 1, giving us 5. Any questions or issues with that?
When would you want to use something like the property where you take like a limit of f of x over g of x and then make it like the limit of f of x over like the limit of g of x, like separate it out that way?
We'll see a couple of those later on today. Most of these all occur when we're dealing with these trig functions, because trig functions get a little tricky. So we'll see a couple of those in probably 10 or 15 minutes.
Okay.
Yeah, we're going to use the multiplication one also. We should use probably use the subtraction one. We're going to use the exponent one today. We're going to use pretty much all those rules that we talked about the other day. We're going to use today. So from now on, we can go ahead and say, as long as x is approaching 0 and we've got anything inside of here, 5x or 12x squared, or 3000x to the 800th power, as long as the denominator is the same, as long as this 5x and 5x are the same, we can just go ahead and say that limit is also going to be 1. Because I could do the u substitution with it, and it's always going to come out the same, where sine 5x squared over 5x squared, that limit as x approaches 0, 1. Still going to happen. Doesn't matter if there's a squared, it's to the 12th power. Doesn't matter if these are 38s in front of it. Still going to come out to be a limit of 1. So you don't need to write out that substitution. We've proven that that works. So let's take a look at this one.
We could move the third power from the sign outside of it, so it would be like sine of 4y and then all of that to the power 3, and we could like cube root it maybe.
Okay, so I like that idea, this first idea of taking the cubed off of the sine 4y, no longer making it sine cubed 4y, but making it sine 4y, the whole thing cubed. That's the same thing. That's what that means. But unfortunately, we can't just like cube root this function as we're trying to find the limit. We can't apply extra stuff to that, unfortunately. So what we need to do instead is just kind of throw that cube that we can see in both the numerator and the denominator around the full fraction. And we had a rule yesterday that said if I have a function being raised to a power within a limit, that I could take that power and pull it outside of the entire limit if I wanted to. And we're going to do that, but not quite yet, because right now this limit, sine 4y over y, why are these x's? I don't know why these are x's. Those should be y's. Sorry. Anyway, this limit here, sine 4y over y, we can't evaluate that until this denominator has a
4.
a four in front of it, right? So let's do that. Let's put a 4 in front of that. If I put a 4 in front of that, what do I have to do with the numerator inside the parentheses? I have to put a 4. So once again, we've almost got the sine 4y over 4y, which would be 1, but we've got this constant that we need to pull out. And so we got to be careful as we do that, because what have we done? We've put a 4 inside of parentheses and cubed everything inside of it. And so when we pull the 4 out of the limit and put it in front of the entire limit, we're not really pulling out a 4, we're pulling out a 4 to the 3rd power, which is what?
54.
64?
60.
Oh.
Yeah. Yeah. So we got 64 times the limit as y approaches 0 of sine of 4y over 4y. And that sine 4y over 4y is cubed. But like we said, we can take that and put it outside the whole limit. And now, rather than having sine 4y over 4y all cubed with the limit, which is not a limit we necessarily know, we have a limit that we do know that we could do a substitution with to turn it into sine x over x if we wanted, but no reason to, because we know this limit inside the brackets is just equal to 1 if we do that. And so we got 1 cubed times the 64 gives us 64. How do you guys feel about that?
Looks good.
Yep.
All right. Any questions on that? Because they're only going to get more difficult.
So the cube goes from like being applied to just the function to being applied to like the whole limit because of how you took out the 4.
Not because I took out the 4, but the cube can go around the whole limit. It was, I got to find it up here. It was one of the rules that we talked about right here. So we did this rule yesterday. If I have a function being raised to a power that's inside of a limit, like the whole, the function to the power is in the limit, I can just do the limit of the function and then raise the answer of that to the power.
Okay.
Yeah, so that was a rule from the other day. You good with that?
Sorry, if
Yep.
you're working with like a question and instead of like cubing it, it's squared, do you have to worry about like it being both positive or negative?
Say that again? If I'm cubing it?
Like instead of cubed, if it was like squared or to the 4th power because it's like raised to an even power, would you have to worry about the answer being both positive or negative?
No, nope. That only apply if we were trying to take the square root of something.
Okay.
Yeah. And Priya, you asked something also, how you want to go over which part the part inside the bracket simplifies to 1?
Yeah.
Yeah, okay. Yeah, so it's the same idea of what we did here, right? That we had the sine 5x over 5x and we let the u equal 5x. I'll write it out here. If we wanted to, since we've got sine 4y over 4y, let's say, we could use u, but why not use x? Because we don't have an x in this problem. Let's let x equal 4y. We'll just make a substitution. And that tells us if y is approaching 0, then x, which is 4 times y, is also approaching 0. And so that will turn this piece of it into the limit as x approaches 0 sine x over x. That's just, this piece right here. And we know this one is the one we proved with the sandwich theorem to be 1. Does that make sense? Does that help?
Oh, okay. I got it.
Do you want us to prove it like that every time we come across a problem like this?
No, you don't need to do the substitution every time. You can just go and say this one with sine 4y over 4y, that one's limit is 1. That's good enough. As long as the argument of the sign and the thing that you have within the denominator are exactly the same and the limit is approaching 0, it's going to be 1 every time. You don't need to write out the substitution. Everybody good?
Yep.
All right, cool. Why don't you guys take a quick look at this one, see if you can come up with what you'd like to do to start it, and I'll give you guys a minute to try it, and then we'll go through it and see where you're at. All right, sorry about that. I'm trying to organize my kids with their school schedules too. So it's gonna happen from time to time. I apologize in advance for the 12 times every class period. It's gonna happen all year long until we go back to the actual class. Anybody have a good idea on this one?
Let's just
For
start
the-
what we kind of did before with the whole bring out a power thing.
Okay, so what power are you gonna bring out?
Fourth power.
Okay, so we're going to use a fourth power here. So let's write this by pulling a fourth power out. But I have a 4 down here. So if I'm going to pull a fourth power around everything,
Square root
that
2.
4 is going to be a little bit of a problem. Yeah, it's going to become a root 2 unless, what is that for? It's just a constant, isn't it? So how about I just put that 1/4 out in front to begin with? Everybody okay with that? Before I pull any powers out, because that 4 is not being raised to any powers. It's just a number, right? It's just a 1/4. That's a 4 in the denominator.
Okay.
Oh, so you're using the constant rule to pull it out? Is that what
Yeah,
you're doing? Okay.
exactly. Yep. And so now I'm going to take everything that's in here and say it's being raised to the 4th power. So I have sine of 3z cubed, and I have z to the 12th. So what does z to the 12th become if I've pulled a 4th power of that out and put it around everything? It just becomes
Z to
a
the
z,
third.
z to the 3rd, right? Because z cubed to the 4th should be z to the 12th, right? And multiply those exponents. Everybody good with that? Those first kind of 2 steps we did there, pulling the 1/4 out and taking the 4th power in the numerator and the denominator and putting it around the whole fraction?
Yeah.
All right, cool. So we've got sine 3z cubed over z cubed. It's almost what we need. So what do we need to put in there in that denominator? We need to put a
3.
Substitute.
3. Yeah. Well, we don't need to substitute yet. The substitution is only once we get those to be exactly the same. Okay. And so if we put a 3 in the denominator, we got to put a 3 up in the numerator as well. And that 3 is not really a 3. That 3 is 3 to the 4th power, right? And so that number is a constant. We want to get rid of that 3 to the 4th power. So we can pull that out to the front as well. So what's 3 to the 4th power?
81.
81. So 81 times the 4th is just 81/4. And now we've got 81/4 of the limit as z approaches 0 of sine of 3z cubed over 3z cubed. And the function inside of my limit is being raised to the 4th power, so I can pull that 4th power out and put it around the entire limit. Everybody good with that?
Yep.
Yep.
All right, cool. So now's the point where we've got the argument of my sine is 3z cubed, the denominator is 3z cubed, and z is approaching 0. If we wanted to write out a substitution to show that this is equal to 1, we could. But since the argument and the denominator are the same, we know it's going to be 1. We don't need to worry about that. We're going to call this 81/4 times 1 to the 4th power, or just 81/4. Any
So
questions?
if you get a situation like this where you have the constant and then the limit, which is equal to 1 to the power, you can pretty much just ignore everything but the constant, because your answer is just going to end up being the constant, or the constant in front times 1 to the whatever power.
Yep, as long as it's this sine of u over u with u approaching 0. Yep.
Yeah.
Yep. As long as you got all that, as long as the argument of the sine and the denominator are the same, right variable over here, it's just going to be 1, and you can ignore them. I mean, I'd like you to write it just so that I see that
Yeah.
you've done that, because if it's on the AP test and you just go from here to equals 81/4, they're going to say, well, what did you do? Why did you get rid of all of this limit thing, all of this limit notation in here? They'll want to see that you made it a 1. But
Wait, does it matter if we put the 4th power inside or outside the parentheses?
no, it doesn't matter one bit. Neither
And
place
then-
is good.
Anytime you see a constant like that in the denominator, would you always try to get rid of it so you're just left with the variable, so it's like easier to manipulate?
Yeah, generally I'd pull out any constants that are already out there. Sometimes the constants that are in there are, convenient and helpful and the one that you need to have in there. But if you pull it out in advance and then you need to put something else back in there, or you need to put the same one back in there, you're just gonna have a fraction to simplify at the end, so it's not a big deal. So easier to just pull them out and not deal with them until the end, is my opinion, but it's up to you. If you left this in here and kept it as a root 2 in there, that's fine. It's just going to be a pain later on. So
When you pulled out like the 81 and made it like 81/4, is that also the rule of constants?
yep, I just pulled out the 3 that's being raised to the 4th power. Yep,
Okay.
constant rule getting pulled out.
Will there be at some point, like, we have to explain, like, in words, like, oh, I used the what was it, the constant something?
I mean, it doesn't specifically have a name. It's you would just say, if I may ask you to explain some stuff in words this year on exams, just because of the nature of how this class is going to have to run from home, where I can't, I mean, you can get a calculator online that'll solve all these problems for you and make it so that you don't have to actually know what you're doing. So I may ask you to explain in words what you're doing, and say, you just say, there's a constant in front of a function inside of my limit, so I can pull that constant out to the front of the limit. I know that's a rule. Any other good mathematician knows that's a rule, so they'd understand what you're talking about, and that's plenty good for me.
Okay.
Yep. All right, let's move on to another one. Similar, but not exactly the same. Any thoughts on what we might do to begin this one?
Pull out the constants.
All right, so yeah, we've got a little bit of an issue with that. Which constants are you talking about? We got 2, we got a 3, and we got a 4.
The 4.
Okay, the 4 is okay. We can take the 4 out if we want to, because the 4 is being applied to everything that's up here, but the 2 is not, it's not a constant that's in front of a full function inside of the limit, right? It's just in front of part of the function. The full function is 2y plus sine 3y, and the 2 is not being applied to the sine 3y, so we can't pull the 2 out. But the 4, we're dividing everything by 4y. So if we want to pull the 4 out as a 1/4, that's great. So sure, we'll do that. We got 1/4, and now we got the limit as y approaches 0 of 2y plus sine 3y over y. So that's a start. But what's the other issue we've got with this one? It doesn't just have the sign of something over a variable, does it? It's got some extra stuff in there.
You could use the sum rule.
All right, we're going to use that sum rule, that addition rule, and we can separate this out into 2 different limits. So one of the limits will be 2y over y, and the other of the limits will be sine 3y over y. And they both need to have a 1/4 in front of them. So we got 1/4 the limit as y approaches 0 of 2y over y, plus 1/4 the limit as y approaches 0 of sine 3y over y. So what can we do with the first limit here, the 2y over y one? What happens there?
Cancel out the y's.
Cancel out the y's.
Yeah, cancel out the y.
Right, if we plug the 0 in, it's 0 over 0, so we got to do some algebra, cancel it out. And what's the limit as y approaches 0 of 2? The limit of a constant is?
2.
A constant.
Well,
the
1/4,
constant.
so 2, 1/2.
Right, so we got 1/4 of 2 for the first one. We'll simplify it in a second, but yeah, it's a half. And then the second one, we've got 1/4, and then we've got the limit as y approaches 0 of sine 3y over y. So what does the denominator there need?
3y. And so then
3.
we multiply the top by 3.
Yep,
and
top
we
by
can plug
3,
it out.
bottom by 3, and then that 3 that's in the numerator, we'll just throw it out here. So that becomes 3/4. The limit as y approaches 0 of sine 3y over 3y. And now pretty much we're done. 1/4 of 2 is a half, plus 3/4 of this limit, and that limit we know is
1.
1. So all we got is a half plus 3/4, or 5/4. Any questions on that one?
No.
Everybody feel good there?
Mhm.
All right, spectacular. Let's see here. Let's move on then. Let's take a look at this one. This one is totally different. You could probably tell that. Doesn't have a sign in it at all. Any thoughts? We're not going to actually use the sign
trig
X over.
identities.
Yeah, we're going to have to do some trig stuff here. So there's no good trig identity just sitting there. I mean, 1 minus cosine x doesn't have something that it specifically equals. Like 1 minus cosine squared x does, but 1 minus cosine x doesn't. Any thoughts on how we might, you know, start
You
with this one?
multiply. Never mind.
You multiply, never mind. I don't know how to do that.
You could multiply by 1 plus cosine of x.
1 plus cosine of x? Okay, that seems weird, but we can try it. Probably a good thing to try since it's the right thing to do. A lot of times, and I know a lot of you guys were in AIM 3 last year, right?
Yeah.
Yeah, and you missed out on a lot of trig probably because something, you know, we had to do school from home for some reason for like 3 months, you know? So one of the things you do with a lot of trig stuff is oftentimes you multiply by the conjugate, and the conjugate of 1 minus cosine x is 1 plus cosine x. And so that's the reason why we're picking 1 plus cosine x. And so what does that effectively do for us with this numerator? What does it turn that into? 1 minus cosine x times 1 plus cosine x, that's just the difference of squares, right? What does it become?
1 minus cosine squared.
Cosine x squared.
Yeah, 1 minus cosine squared x, and we still got an x and a 1 plus cosine x in the denominator. Okay, cool. So what? Why do I care? What good did that do?
Sine squared x.
All right, so we've got a trig identity here. 1 minus cosine squared x is equal to sine squared x. That comes from the first of our Pythagorean trig identities, right? Sine squared plus cosine squared is 1. So 1 minus cosine squared is sine squared. So now we've got the limit as x approaches 0 of sine squared x over x times 1 plus cosine x. Is this enough simplification? Are we good? Can we plug in 0 now and get something that's not indeterminate?
No.
Nah, if I plug in 0, I still get 0 over 0 times 2, which is 0 over 0. So it's still indeterminate. So now what?
We can pull the 1 plus cosine x out from the bottom.
That's a good idea. I like that idea, but the 1 plus cosine x is not a constant because it's got that variable of x in it. So we can't pull that out. If it's got a variable in it at all, it cannot be removed from the limit. So it's got to stay in there.
Maybe this is where we could use the division rule and separate the two limits.
Okay, so that's a good thought also. If we separate them, the top one is 0, which is fine, but what's the bottom limit going to equal? 0 also, and that rule specifically said that only works if the bottom limit, if the denominator's limit is not 0, and it is. So.
Oh, that's right.
Yeah, it's a good idea. We're going to have to use one of those rules, just not the division one.
Would we separate it to sine x over x times sine x over 1 plus cosine x?
That sounds like a good place to go. Seems smart because sine x over x is a limit that we know, right? And that one, even though it's 0 over 0, we know its value. So here's sine x over 1 plus cosine x, right? We've just rewritten this as sine x over x times sine x over 1 plus cosine x, put the sine squared into two different signs. And now this is a multiplication of two different limits, which can be rewritten as two separate limits. So far, good?
Yep.
Yeah.
All right, so the first one we know. What's the first one?
1.
1. And the second one, well, let's plug it in and see what happens. What's the numerator there? It's 0. Hopefully the bottom's not also 0. What's the bottom? It's 1 plus cosine of 0, which is
2.
1.
1 plus
Yeah.
1, 2.
1 plus 1 gives us 2. So what does this limit come out to be? This is okay. 0 over 2 is fine, right? That's not indeterminate. That's just 0. And 1 times 0 is
0.
0.
0.
Any questions on that? Okay, this is another one that I'm going to want you to have memorized. So memorize limit as x approaches 0 of 1 minus cosine x over x. It is always 0. And if you flip that around to be cosine x minus 1 over x, that's also 0. So just be aware of that. You can basically do the same process to prove it. We're not going to bother to do that, but cosine x minus 1 over x, its limit as x approaches 0 is also 0. Everybody good?
Yeah.
All right, we're going to do a couple more here, 3 or 4 more, hopefully. Get through the rest of these trig ones, and then hopefully we have enough time to do that, and then we'll get out of here. Thoughts on this one? Looks pretty similar, right?
Multiply by 10 over 10.
All right, let's multiply by 10 over 10 because that's going to turn this into 1 minus cosine 10x over 10x. And if I put a 10 up here in my numerator, what can I do with the 10 that's in the numerator?
Bring it to
Move it
the
out.
front.
Take it out to the front, 10. Limit as x approaches 0. Now I've got 1 minus cosine of 10x over 10x. Is that 0? That inside
We
part?
could prove it with substitution.
We could prove it. We should probably do that once since we haven't done it with the cosine one. If we let u equal 10x, then what is u approaching? As x approaches 0, u is approaching 0, which gives us 10 times the limit as u approaches 0 of 1 minus cosine u over u. That one we just memorized to be 0. We got 10 times 0 or 0. Pretty straightforward, or anybody have any questions on that?
Nope.
All right. Cool. Let's do another one then. Another nice easy one, nice little simple looking one, right? Looks almost the same. Any thoughts? No one?
Maybe try and pull out exponent. I don't know.
Yeah, it's a pain, huh? It's a little bit of a mess there. Anybody notice something about, let's see here, 1, 4, 6, 4.
Multiply by 12.
Whoa, I'm not sure what happened. I just lost my screen. I think I just ended my screen sharing. Did it just stop sharing the screen?
Yeah, it's back now.
All right. Okay, there we go. Cool. What do you notice about those coefficients there? 1, 4, 6, 4, and 1.
They're in sort of like that, what's it called? Remember that numbers with like a
Pascal's triangles.
Pascal triangle.
Yeah, Pascal's triangle, exactly. 1 second here. I gotta deal with my kids here for a second. Noah, you were supposed to be in a class.
Yeah, but there's only like 3 minutes, and you reason.
Guess I should mute myself sooner before I start yelling, huh? Oops. All right. So this is Pascal's triangle. Everybody familiar with Pascal's triangle, or anybody need some help with that? We're going to talk about it. Here's Pascal's triangle.
A little bit.
Everybody should have seen this at some point in, like, you know, 3rd grade or something. I think that's when you first start talking about this, right? Something like that. Right. We start with a 1, we put another 1, another 1. 1's all the way on the outside of the triangle. And then 1 plus 1 gives us this 2. 1 and 2 gives us 3. 2 and 1 gives us 3. Another 1 on the outside. 1 and 3 is 4. 3 and 3 is 6. 3 and 1 is 4. And so on, right? 1 and 4 is 5. 4 and 6 is 10. Blah, 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 blah. Pascal's triangle, right? Somebody was like, hey, look, here's this cool triangle with all these numbers in it. And then somebody realized that as you go through and you try to do, let's say, a plus b to the 0 power, what do you get if you do a plus b to the 0 power?
1.
You get 1. You get 1. What about if you have a plus b to the 1st power? What are the coefficients? They are 1 and 1, right?
Yeah.
And what about this next one? If we did a plus b to the 2nd power, that's a squared plus 2ab plus b squared, right? What are the coefficients?
Yep.
They're 1, 2, and 1. And guess what the coefficients if you're doing a plus b to the 3rd power are? There 1, 3, 3, and 1, right? It's a plus b to the 3rd is, and I'm going to run out of room here probably, a cubed plus 3a squared b plus 3ab squared plus b cubed, right? And the coefficients of 1, 4, 6, 4, 1 come from a plus b to the 4th. The way we alter this, if it's a minus b, let's say, to the 4th power, that should be a to the 4th and then minus 4a cubed b plus 6 a squared b squared minus 4ab cubed plus b to the 4th, where they just alternate signs. And that's exactly what we've got here, is we've got a 1 and then a minus 4 and then a plus 6 and then a minus 4 and then a plus 1. 1, 4, 6, 4, 1 with alternating signs. And this should, in the numerator, factor out to become 1 minus cosine x to the 4th power. Okay. This whole thing here is like the binomial theorem. This is binomial theorem expansions. So you should be able to expand out any binomial using these as coefficients. Does that sound familiar to people?
Yep.
Yeah.
All right. Cool. So if we factor this down to 1 minus cosine x to the 4th, and I've got an x to the 4th in the denominator, what do we end up with? Limit as x approaches 0 of 1 minus cosine x over x, all raised to the 4th. And what's the limit as x? The limit as x approaches 0 of 1 minus cosine x over x is 0. We got 0 to the 4th, or just 0. Everybody good there?
Yes.
Yep.
All right. Let's do another one. So take a look at this one and see if you can figure it out. See if you can come up with an idea here. Any ideas on this one? What do you guys think?
Could we try splitting it into two different limits?
What two limits do you want to split it into?
Like the limit is y approaches 0 of sine of 4y, and then it's the division rule.
The division rule. Okay, so we got a problem with the division rule again, which is
That's 0.
that's 0 if we plug in 0 to the denominator. So that's not going to work. But I like your idea of splitting it up. So let's split it up, but leave it all within the same limit. I'm going to write it like this: sine 4y over 1 times 1 over sine 10y. Is that okay?
Yeah.
I can do that, yeah. Okay. So I could separate this out using multiplication if I wanted to into two different limits, but the second one is going to be 1 over 0, which is a problem. But what could I do to the denominator of the sine 4y to make it one that I know how to deal with?
You can make it 4y.
Okay, I can multiply by 4y, right? But that means I need to multiply the top by 4y. Now I'm going to hold off on that a second before I actually do the numerator multiplication. We know we need to do it. We'll do it in a bit. What about this one? What could I put in the numerator up there to make that one that I can deal with?
10y.
All right, if I put a 10y up there, that's 10y over sine 10y. And we knew that x over sine x, that one's limit was 1. So if we did that, that should be 2. So what have I done? First off, I've multiplied the numerator of this whole thing by y, and I've multiplied the denominator of this whole thing by y. Those cancel out, right? I mean, I need to have them there, but that's okay. I multiplied the top by a y, and I multiplied the bottom by a y. No algebraic issue there. Would you guys agree?
Yeah.
Yeah.
Okay. I've multiplied the top by a 10, but not the bottom. So I do need to throw a 10 in down here. And I multiplied the bottom by a 4, but not the top. So I need to put in a 4. So now I've multiplied top by 40y, bottom by 40y. Perfectly okay, right? Like multiplying by a 1. Everybody good there?
Yep.
Okay, now I got this 4 that I don't need and this 10 that I don't need. I'll take those out to the front. We'll reduce the fraction in a bit. We got 4/10 of the limit is y approaches 0 of sine 4y over 4y. And the other one, which I can multiply it by, is the limit is y approaches 0 of 10y over sine 10y if I separate those out using the multiplication rule. And what do we get? We get 2/5 times 1 times 1, or just 2/5. Any questions there?
So for
Wait,
the,
so. Oh, sorry.
oh no, it's
You can
okay.
go first.
So for where you had the 4 and the 10 on the numerator and the denominator, you didn't have to put the y because you already had a y from when you multiplied the 1s by 4y and 10y.
Correct. Yep.
Okay.
Yep. Those y's, those y's were good enough for the whole thing, right?
Okay, that was my question.
Okay, perfect. All right. I think we're going to do one more. And then this will be our last one for the day, which is probably good since I think we got like 5 minutes of class or 7 minutes of class or something like that. Any ideas there?
Would you want to split up the tangents into sine over cosine?
Sure, that sounds like a start. limit as x approaches 0 of sine 3x over cosine 3x, all over sine 4x over cosine 4x. Sounds good to me. I don't really like having a fraction divided by another fraction. Could I rewrite this as a limit as x approaches 0 of sine 3x over cosine 3x times cosine 4x over sine 4x?
Yeah.
All right. So now, part of it, sine 3x and the sine 4x in the denominator, is pretty similar to what we were dealing with a minute ago with this one, right? So maybe I write those ones separately. Limit as x approaches 0 of sine 3x over 1 times 1 over sine 4x. And what about the cosine 4x and the cosine 3x? Are those ones going to be an issue?
No, because they're cosine.
Right, no, because they're cosine. If I plug in 0 to cosine 4x, you know, that's cosine of 0 divided by cosine of 0. That's just 1, isn't it?
Yep.
So that's not going to be an issue.
Yep.
So what do I need to do with this first one? Just the same thing I had before, right? Put in a 3x down here and put in a 4x up here. And the x's are good. They cancel each other out. I just need the 4 and the 3. And so the constant that I'll pull out is 3/4. 3/4 times 3 different limits. The limit as x approaches 0 of sine 3x over 3x. The limit as x approaches 0 of 4x over sine 4x. And the limit as x approaches 0 of cosine 4x over cosine 3x. And what does that give us? It gives us 3/4 times, this first limit is
1.
Second limit is
1.
And the last limit is
1.
Also 1, right? Cosine of 0 is 1. Cosine of 0 is 1. That's just 1. So our final answer is 3/4. Any issues or questions with that?
Nope.
All right. So before I kick you all out of here, the limits that we should know from today are these ones, right? Sine x over x is
1.
1.
The limit as x approaches 0 of x over sine x is
1.
1.
And the limit as x approaches 0 of 1 minus cosine x over x is
0.
0. Limit as x approaches 0 of, I just mentioned this one, we didn't actually use it, but cosine x minus 1 over x is 0. And I'm going to add 2 more in here that have to do with tangent that we could prove, but I think might be sort of evident from the one we just dealt with. Tangent x over x is just 1 because the cosines don't really matter. And also the limit as x approaches 0 of x over tangent x is also 1. So I need you guys to know those 6 trig limits and have those memorized.
All right.
All right. That should be it for today.
I can see the screen in my audience. What was the last one? Can you just get out of that?
I'm sorry, I could not understand what you were saying.
Could you repeat the last limit, like in words?
I have to, maybe can you type it in the chat, because I can't. Yeah, I can't understand what you're saying. It's cutting in and out. Oh, the last, yeah, sure. Yeah, the last one's the tangent ones. Okay, yeah, so the limit as x approaches 0 of tangent x over x equals 1, and the limit as x approaches 0 of x over tangent x equals 1. And those ones we can prove just by using the sine x over x ones if we wanted to, right? Because if you just throw a cosine into the denominator here, that becomes tangent x over x, and the cosine of 0 is just 1, so it doesn't affect it.
Can you go to the previous slide for one quick second?
Sure. You have a question on, or you just needed to see it?
Let me see. Hold up. Why is the limit of cosine 4x over cosine 3x 1?
Plug in 0. So what's the cosine of 0? It's 1. And in the denominator, the cosine of 0 is also 1. So it's just 1 over 1.
Okay, thank you.
That one's not actually indeterminate. You can just plug it straight in. So.
Okay.